All right, we're going to review horizontal asymptotes, remove misconceptions about them, and define the limit at infinity. This is a 2.6 pre-class video. So in pre-calculus, we studied horizontal asymptotes. Here's two graphs that both have a horizontal asymptote. The equation of this horizontal asymptote is y is equal to constant. We'll call that constant capital L. And the definition was the line y equals L is a horizontal asymptote of f of x if y approaches L as x approaches plus infinity or minus infinity. Now the way we'll talk about it is the line y equals L is a horizontal asymptote of f of x if the limit of f of x as x approaches infinity equals L, or the limit of f of x as x approaches negative infinity is equal to L. And the meaning of this new definition is the values of f of x can be made arbitrarily close to L by requiring x to be sufficiently large, either in the positive direction or the negative direction. So let's look at an example with this particular function. And here's its graph. And this has a horizontal asymptote. There's the dotted line showing the horizontal asymptote. And the line is y equals to 3/2. And the way we can write that is the limit of f of x as x approaches infinity is equal to 3/2. And also, limit of f of x as x approaches negative infinity is also 3/2. So if you go in either direction, if you get really big in the positive x direction or the negative x direction, then our function values approach 3/2. Here's another function, and here's its graph. This does have a horizontal asymptote, and this is the first misconception I want to clear up, is that a function can cross its horizontal asymptote. So the horizontal asymptote is that y is equal to 0, so the limit of f of x as x approaches infinity is equal to 0. As x gets really big in the positive direction, our function values go to 0. So there is a horizontal asymptote. And also, as you approach negative infinity, our function values get arbitrarily close to 0. So here's one example where your function can cross your horizontal asymptote and actually crosses an infinitely numbered times for this particular function. Here's another function, and there's its graph. And this is the second misconception I want to remove, is that there can be two different horizontal asymptotes for a single function. So there is one at y is equal to 3, and one at y is equal to negative 5. So as x gets really big in the positive direction, our function values approach 3, so the limit of f of x as x approaches infinity is 3. And as x gets very large in the negative direction, our function values get arbitrarily close to negative 5, and so the limit of f of x as x approaches negative infinity is negative 5. So this is an example where you can have two different horizontal asymptotes for a single function. All right, so how do we find these limits at infinity? Well, one way is to look at a plot, but it would really be a guess if we said the limit at infinity is a particular value, because when we take a plot, our window is only so big. We can't zoom out infinitely far to see what the limit is. Another way would be making a table, let x get really, really big and see what the function values approach. But again, this would be a guess. The way we'll look at limits at infinity in class will be to combine algebra with limit laws to get an exact answer. All right, so that's what's happening in the next class. Hopefully, this video helped you with these three objectives.